World of quantum mechanics, we're going to tackle the relationship between Heisenberg's uncertainty principle and, well, wave function collapse. It can get pretty perplexing.
Oh, absolutely. Quantum mechanics definitely throws some curveballs at our, classical
Yeah.
intuition. It seems strange, but what's really remarkable is how it all fits together.
Yeah.
We're going to explore how that inherent fuzziness, the uncertainty principle, isn't just some separate rule. It's actually deeply connected to what happens when we try to look, when we make a measurement, and that wave function seems to just snap into a single state.
Exactly. And we've looked at some great source material that really digs into these concepts. So our mission today, let's try and pull out the key insights. Understand how this fundamental quantum uncertainty, this fuzziness, plays out in the very active observation of measurement.
Sounds good.
Okay, let's unpack this. Maybe start with the star player before any measurement happens. The Schrödinger wave function. What exactly is this psi thing describing quantum particles?
Right. So before we actually go looking, before we measure anything, a quantum particle, think of an electron. Maybe it doesn't really have definite properties like, say, a tiny billiard ball does.
Okay.
Instead, its state is described by this mathematical thing called the wave function, usually written as psi. You can kind of think of it as, well, maybe like a container holding all the possibilities for that particle.
A container of possibilities. Interesting. So it's not like a physical wave, like ripples on a pond.
Exactly right. It doesn't ripple through our normal space in the same way. It exists in what physicists call configuration space. Now, for just one particle in 3D space, that's not too far off from our everyday space. But when you have multiple particles interacting, the configuration needs to track the positions of all of them at once. That means this space becomes much higher dimensional, hard to visualize, but mathematically crucial. And importantly, the wave function uses complex numbers. They're not just regular numbers, they have a magnitude and a phase, like a direction on a compass. This phase is key because it allows for interference effects.
Interference? Like waves adding up or canceling out?
Precisely. Just like water waves or sound waves can interfere. This complex nature is what allows a particle to, well, effectively be in multiple states at once.
So before we measure, the particle is just this, probabilistic soup. All potential locations and speeds mixed together.
It's not a bad analogy, yeah. A probabilistic soup. And even weirder, it can be in a superposition. That means it's literally a combination of multiple possibilities simultaneously.
Multiple places at once.
Mathematically, yes. The wave function allows for that. It encodes the probability of finding it here and the probability of finding it there, all mixed together.
Wow. Okay,
Yeah.
That is mind-bending. So this wave function, this mix of possibilities, just evolves over time until we do something.
Exactly. Before any measurement intrudes, the wave function evolves smoothly. Predictably, even. It follows a famous rule called the Schrödinger equation. So the probabilities change over time in a perfectly deterministic way.
Okay, so we have this evolving wave function describing probabilities. Got it. Now, let's bring in Heisenberg, the famous uncertainty principle. What's the core idea? Why can't we know everything perfectly?
Right, Heisenberg. Well, the uncertainty principle, probably the most famous version, deals with position, let's call it x, and momentum p, that's like mass times velocity. It tells us there's a fundamental limit. You just cannot know both of these properties with perfect simultaneous precision.
There's a formula, right?
There is. It's x times O is greater than or equal to divided by 2.
Okay, break that down. X and X.
X is the uncertainty or the spread in our knowledge of the position. F is the uncertainty in the momentum. And X is the reduced Planck constant. It's a tiny, tiny fundamental constant of nature. The point is, the product of these uncertainties can't be zero. It has a minimum value.
So this isn't just about having clumsy measuring tools, like if we built a better microscope.
Nope, not at all. That's the really deep part. It's not a limitation of our technology. It's baked into the very nature of quantum reality. It comes directly from the fact that quantum particles also behave like waves.
Ah, the wave-particle duality thing. How does being wave-like lead to uncertainty?
Okay, think about a simple wave like a sound wave. If you want a wave that's really concentrated in one place, like a short, sharp blip, what do you need to make it?
Like lots of different frequencies combined.
Exactly. To make a sharp pulse localized in time or space, you have to mix together a wide range of frequencies or wavelengths. Now, back in the 1920s, de Broglie proposed that particles have a wavelength, and it's related to their momentum specifically, inversely proportional.
Okay.
So if a particle's weight is very localized, meaning we know its position precisely, small x, it must be made up of a broad range of wavelengths. And a broad range of wavelengths means a broad range of momenta, large
That
time.
in the other way around.
Yep. If you have a wave with a very pure tone, a very specific wavelength, meaning precise momentum, small whoop, that wave has to be spread out over a large distance, large stacks. You can't have both sharp position and sharp momentum simultaneously because of this wave nature. It's an inherent trade-off.
That makes a lot of sense with the wave picture, like you said, a short sound burst versus a long pure note.
Mm.
Okay, so the wave function holds these possibilities, and it inherently has this uncertainty built in. Now, what is this collapse people talk about? What happens when we actually measure something?
Right, the collapse. It's sometimes called the measurement postulate. It describes what happens the moment we do measure a specific property, like position. Suddenly, the smooth evolution, according to Schrödinger's equation, stops.
Doves.
Well, it's interrupted. The wave function abruptly and discontinuously changes. It goes from being that spread out superposition of many possibilities into just one single definite state, the one corresponding to the result we actually got from our measurement.
Whoa, okay. Abruptly. Discontinuously. That sounds really different from the smooth wave evolution.
It is. It's quite jarring conceptually. Imagine our electron again, its wave function spread out. We set up a detector to find its position, and bam, the detector clicks at a specific spot. Let's call it x0.
Okay.
In that instant, according to this postulate, the electron's wave function is no longer spread out. It becomes sharply peaked right around x0. It basically says, okay, the electron is here now. The probability of finding it anywhere else drops to 0, at least for that moment right after the measurement.
So all those other places it could have been, according to the wave function, they just vanish. Poof.
According to the standard, or Copenhagen interpretation, yes, they vanish. The measurement forces the system to choose one outcome from the possibilities encoded in the wave function. And which outcome it chooses is probabilistic.
Probabilistic, meaning random.
Fundamentally random, yes. We can predict the probability of finding the electron at x0 that's given by the intensity or the square of the magnitude of the original wave function at that point. But for any single measurement, the specific outcome is unpredictable. And here's the kicker. This whole collapse process, it's not described by the Schrödinger equation. It's like an extra rule we add on for measurements.
Okay, so we've got the wave function, probabilistic description, the uncertainty principle, fundamental limit, and collapse, sudden change on measurement. Now, connect them for me. How does the uncertainty principle specifically relate to this collapse event?
Okay, this is really the core connection. The key idea is that the wave function before the measurement already respects the uncertainty principle. It's built in. If the initial wave function is naturally quite localized in position, so x is relatively small just due to how the system is prepared, then the mathematics of that wave function automatically mean its momentum distribution is spread out. X is relatively large, and vice versa. The initial state always satisfies x sub O2. The fuzziness is inherent from the start.
Okay, so even before we look, the description follows the rule.
Absolutely. Now, think about measuring. Let's say we decide to measure the electron's position very, very accurately. We use a really precise detector. What happens to the wave function?
You said it collapses, right? To be sharply peaked at the measured position.
Exactly. So after the collapse, the uncertainty in position x becomes very small because we've just pinpointed it.
Right. We know where it is now, pretty much.
But wait. Remember Heisenberg, x go Po2. If our measurement forced ducts to become tiny, what must happen to ek, the uncertainty in momentum?
It has to get bigger to keep the product above that minimum value.
Precisely. By measuring the position accurately, we've inevitably made the momentum much more uncertain. The very act of nailing down the position seems to destroy the information we might have had about its momentum, forcing it into a state with a wider range of possible momenta.
Wow. Okay, so the measurement doesn't just reveal a position that was already there, hidden. It actively changes the state, specifically making the momentum more uncertain because we measured position.
That's a really good way to think about it, yes. It forces the system into a new state that still obeys the uncertainty principle, and conversely, if we measure momentum precisely.
Let me guess. The wave function collapses to a state with a very small cup.
Correct.
Which means x, the position uncertainty, must become large.
You got it. Knowing the momentum precisely smears out its possible location. It's like this quantum seesaw. Push down on the uncertainty of one variable, and the uncertainty of its conjugate partner goes up, always respecting that tier 2 limit.
Okay, that connects things much better. The wave function starts out obeying the principle, Measurement forces a collapse to a specific value for the thing you measured. But that new collapse state also has to obey the principle, which affects the other variable.
You've nailed it. That's the interplay. Now, we can maybe dig just a little deeper into some of the concepts here.
Please.
We mentioned the wave function is a complex valued probability amplitude. That word amplitude is important. It's not just the probability itself, which is the amplitude squared. The complex nature, the phase, is critical for things like quantum interference.
Interference, that's the double slit experiment, right? Where one particle seems to go through both slits.
Exactly that. The wave function components going through each slit interfere with each other because they are complex amplitudes with phases. That's how you get the characteristic pattern on the screen. This superposition being in multiple states at once is possible because the underlying maths, the Schrödinger equation, is linear. If you have two valid solutions, their sum is also a valid solution.
And you mentioned looking at the wave function in different spaces, position and momentum.
Yes. So we usually think about x, the wave function in position space. Its square gives the probability density of finding the particle near position x. But you can represent the exact same quantum state using a different function, often written in momentum space. The square of this function gives the probability density of the particle having momentum near p.
So two ways of looking at the same thing.
Exactly.
Yeah.
And they're not independent. They are mathematically connected by something called the Fourier transform.
Fourier transform. I've heard of that in like signal processing, breaking down signals into frequencies.
That's the one. It's fundamental here too. And guess what? The Heisenberg uncertainty principle is a direct mathematical consequence of this Fourier transform relationship between position and momentum representations.
Really? Oh.
It's a basic property of Fourier transforms. If you have a function that's very narrow in one domain, like position space, meaning x is small, its Fourier transform must be wide in the other domain, momentum space, meaning ape is large, and vice versa. A wide function has a narrow transform. That mathematical trade-off is the uncertainty principle. X apo2 falls right out of the mass of Fourier transforms applied to the wave function. So the uncertainty isn't some weird extra rule bolted onto quantum mechanics. It's embedded in the core mathematical structure. Precisely. It's in the DNA of how we describe quantum states. Which brings us back to collapse again. When we measure, we force the system into a state that highlights one variable, like position, but that state mathematically must reflect the corresponding uncertainty in the Fourier conjugate variable, momentum.
You also hinted earlier about a measurement problem. Is the collapse idea itself debated?
Oh, hugely. It's one of the deepest foundational puzzles in quantum mechanics. What exactly constitutes a measurement that triggers this collapse? Does it need a conscious observer? Or just interaction with a big macroscopic device? How does the smooth Schrödinger evolution suddenly get interrupted by this probabilistic jump?
But that sounds like a big question mark.
It really is. There's an idea called decoherence, which is very important. It explains how a quantum system interacting with its environment, like air molecules, photons, whatever, quickly loses its nice quantum superposition properties and starts to look classical. The different possibilities effectively get tangled up with the environment in complex ways.
Does that solve the collapse problem?
It helps explain why we don't see, cats that are both alive and dead in the everyday world. It explains the loss of interference, but it doesn't fully explain why we get one specific outcome rather than another when we measure. The selection problem remains.
So what else are people thinking?
Well, there are different interpretations. The many-worlds interpretation says collapse never happens. Instead, the universe splits into branches for every possible outcome.
Whoa.
Yeah. Then there's pilot wave theory, which suggests particles do have definite positions, guided by the wave function, and measurement just reveals them. And objective collapse theories try to modify the Schrödinger equation itself, adding tiny terms that cause collapse automatically, especially for larger systems. It's still a very active area of debate and research.
Fascinating. So many different ways to try and make sense of it. But okay, bringing it back to our core link here. No matter how you interpret collapse, or if it even happens in some interpretations, the relationship dictated by the uncertainty principle holds.
That's the key takeaway. Any description of the state after an interaction that yields a definite result for one variable must conform to the uncertainty limits for its conjugate variable. Measurement, in essence, forces the system into a state compatible with Heisenberg's rule. It makes one property definite, but at the cost of uncertainty in the other.
Okay, let me try and summarize then. We have the wave function describing quantum possibilities. It inherently includes the fuzziness of the uncertainty principle right from the start. When we measure, something happens, let's call it collapse for now, and we get a specific outcome for the measured property. But this new state, the result of the measurement, still has to obey the uncertainty principle. Gaining knowledge about position, say, forces greater uncertainty onto momentum, and vice versa.
That's an excellent summary. You've captured the dynamic perfectly. Measurement transforms quantum possibilities, constrained by uncertainty, into a classical-like reality, one specific outcome, but always under the watchful eye of Heisenberg's principle.
This has been incredibly insightful. It really drives home just how counterintuitive yet internally consistent the quantum world is. So maybe a final thought for our listeners to mull over.
Look for it.
Consider this inherent uncertainty, this fuzziness right at the fundamental level of reality. How does that connect to the seemingly solid, predictable, deterministic world we experience every day? If everything is probabilities and uncertainties down there, how does our macroscopic reality emerge? What does this fundamental limit on knowledge really tell us about the nature of reality itself?
That's the big question, isn't it? Definitely something to ponder.
Absolutely. Thanks for joining us on this deep dive. We hope you found it as fascinating as we did, and maybe it sparks further curiosity about the amazing world of quantum mechanics.